my office and wait for students to come in and ask me questions. So if you have a question about this class or any math or science class that you're taking, we can help you out. If you haven't been to the Success Center before, just walk in the main doors of the library. You'll be facing the stairs. Walk towards the stairs, but then veer right before going up, and you'll be walking right into the Success Center. It's a windowed in area there. To find me, you go into the Success Center all the way to the back and around the corner. The first office is Josh. He can help you with math and physics. The second office is mine. I can help you with math, physics, chemistry, biology, and stats, which happens to be one of my favorites. So we are there to help you Monday to Friday, 8 to 4, and math and science help is all drop-in. So you can just come in with a question. You don't need to email first. You don't need to make an appointment. You can just say, I'm stuck on what this means, or I'm stuck on this one question, or we did this example in class, but I don't really understand how Emily got from this line to this line. Anything like that, come on in and we can help you out. If you walk into the Success Center, you'll see it is set up with tables. That is meant to encourage group work. And I highly encourage you get a study buddy or a study group, because as soon as you start explaining something to someone else, it will make more sense to you. And I know stats is kind of a weird combination of like some theory with some math thrown in, and not a lot of people are really good at both. So as soon as you have somebody that you can talk out your ideas with, that's actually really going to help you out. So I highly recommend you do that, but whether you're working on your own or in a group, you are welcome to use that as a study space anytime. And then we're right there to help you if you get stuck on anything. So it's convenient for that as well. If you need help with English or writing, either because you're taking an English or communications course, or maybe you have a lab report or something to write, we have help for that as well. So when you walk into the Success Center, the first office on the right is Shannon, or the office just past mine is Carolyn. And they will take an appointment to work through your whole essay or rules of commas or Shakespeare, whatever you do in English classes these days. They will help you with that. You can either scan the QR code on their door, or you can just go to the Success Center website and find the link there to make an appointment.
Which is on our Moodle page.
There you go. I just scroll down and we can see the appointment. Yeah, so there's Kelowna, and then if you scroll down to English and writing, there's my email address if you want to email me for something. But there's book an appointment with Shannon, book an appointment with Carolyn. There, voila. If you want to make an appointment for English or writing. So lots of information there. What was that on my points?
You need a cheat sheet.
Well, I've done this 18 times. So I think that was all of my points, the English and writing. Yeah, so then I just go back to the math and science and say, you essentially already paid me by paying your tuition. So it's free help available just over in that building over there. Are there any questions?
All right.
Okay.
Thank you, Kate. Make that 19 times.
Yeah, something like that. I hope to see somebody soon.
Bye, Kate. Thanks. Isn't it incredible? It's like math, stats, physics, chemistry, biology. I don't know how, but she does, and it's incredible. But so she's very familiar with the course and all the common issues that we have in this course. Okay, let me just make sure. I'm already recording. I caught a little snippet of that. So nice. Okay, I'm sharing my screen. That's all good. Okay, I did it. All right. Good morning. Good morning. So today we're going to start chapter 2. So last day as a little bit of review before we officially get started. It was last week after all, so it's been a little while. The main thing that we introduced was variables, right? Talking about variables. So a variable or variables, they're the columns in your spreadsheet if you're thinking about a spreadsheet, which I think is a nice way to kind of imagine it, right? That's usually how we collect data. And so the columns in your spreadsheet, they're the variables. And we have two different types of variables, right? We talked about some other ones, but what I need you to carry forward is we can have a numerical variable. Oops, that's not very nice, is it? If I zoom in, it doesn't help. Categorical is the other type of variable. We introduced some other terms, right? Instead of numerical, we could say quantitative, and instead of categorical, we could say qualitative. But I find that they're a little bit more confusing than they need to be. And so, right, we're going to focus on numerical variables today, right? And so we also talked about the response variable. A response variable is what? That's going to be the variable that I'm most interested in my studies, right? And so there's always something that I want to learn about. Okay? And so it's going to be the variable of interest. Whereas the explanatory variable, I'll bump it over here. The explanatory variable, so we can have more than one explanatory variable. Okay. Those are variables that we collect to help explain changes in the response variable, right? And so variables collected to help explain. There's a clue there, right? All these clues in the words to help explain changes in the response variable. What else did we talk about? We talked briefly about data collection and how important it is to have a sample that's representative of our population. If we want to draw conclusions about the population, which we already established is kind of the goal of statistics overall, is to take a sample to learn about the population. Well, the only way that we can do that properly is if our sample is representative of the population. Now, the best way to do that is to collect a random sample, right? And so random sampling or an SRS, as we introduced it last day, a simple random sample. Okay. We talked about a stratified random sample and a cluster sample. We talked about other samples, but from here on out, we're going to focus on just a simple random sample. And so random sampling allows us to assume our sample is representative of the population. Our sample is representative of the population. Nice try, Emily. I forgot. Where did it go? There. I posted some assignments. Hopefully you saw them. Right. I'll be posting assignments pretty much after every class. So it's worthwhile checking in, and I give you a week to do it. And like I mentioned last day, hey, maybe I did say it last day. They'll come up on your dashboard, or hopefully it looks like this for you too, right? And so I have other courses, obviously, but all right, so some of those are ours and some of those are not. Okay, these are not the actual due dates. Okay, I have to tell it what it is, so sometimes I muck it up. But if you click on the assignment, the due date that shows when you enter the assignment is the actual due date. Especially if I bump a due date, right? If everyone comes to me and says, we need more time. We're so swamped. That's totally fine. Right, then I'll bump it, but it won't show up here. Okay, they're not connected, sadly. We'll get there. We'll get there. Too fancy for us. Okay. So I'll post an assignment after today. Maybe. We'll see how far we get. Okay. So random sampling, very important. I'm pausing because there was something else I wanted to say about the assignments. Oh, just now I remember. You can go into them, you can open them, you can try them, you can close them, you can go back to them up until the due date, right? And so, and then at the due date, I think it'll submit whatever it is you have entered, right? And so even if you have submitted it, right, it'll still let you resume, which is kind of confusing, but just trust that you've submitted it and it's over. All right. So any questions about last week? Today, chapter 2. All right, we're kind of moving through this this path, right? Last day we introduced how do we talk about data, that's important. Then how do we collect data? Now, what if we've collected data? Now, if I have to summarize data, that's the next thing that we do. And so this week we're going to talk about summarizing data, okay, in chapter 2. We're going to start with numerical data, right? So now I have measurements, right? I can talk about the average. That's going to be an important part of what we're doing this week. Okay, and so we're talking about numerical data, and then section 2.2 is on categorical data. There's not a whole lot that we can do to summarize categorical data, so it's kind of boring in that sense, and so it's going to be a little bit shorter, whereas there are a lot of things we can do to summarize numerical data. Okay. One of the ways that we have already seen, right? So from last week, we saw scatter plots already, right? And so scatter plots are useful for visualizing the relationship between two numerical variables. I think I might have mentioned last week that we will consider, as long as the response variable is numerical, we can make a scatter plot with an explanatory variable that's either numerical or categorical, but that's kind of way off in the distance. But for now, let's just say it's for two numerical variables. Okay. So these are bubble charts, and pretty sure this site has changed. Oh, and it won't let me even go there. Okay, well, that's okay. But there are lots of these kind of animated visualizations. And one of the most famous statisticians, and he's not just my favorite because he's Swedish, but Hans Rosling. So you can watch any talk by Hans Rosling. Sadly, he's passed away recently, or kind of a couple of years ago now, I guess. But he does these very animated, kind of demographic summaries like this. Okay, his look even better than this bubble chart. Right? But so here we've incorporated a lot of information, right? And one of the main things that we're going to need to keep in mind as we are visualizing data, okay, so this is a way of visualizing data, right? In the background, we have a spreadsheet of some sort, of course. But when we're visualizing data, one of the main things that you want to remember is you should be able to just look at it briefly and kind of understand what's going on, right? There can be some nuances, but you don't want to generate a graphic that you have to explain to someone, right? The idea is you glance at it and you understand roughly, right? Depending on the context. So in this case, we've got the life expectancy in years and the children per woman, which they're using as a measure of total fertility, okay? And then, of course, in the background, we have the year, okay? And we've got these kind of sizes of dots. For me, it's not really clear what those sizes are. This is obviously just an excerpt from the website, so they probably explain it. But right here, what do we see? We see that there's this kind of negative relationship, right? We could probably model it with a line, seems reasonable, right? And so what does that mean? As the life expectancy, or maybe as the children per woman or the total fertility increases, right, then the life expectancy is decreasing, okay, in 2011. Then you can go to 2012 and you can look at that relationship, et cetera, et cetera. Okay. So we've already seen a scatter plot. Do life expectancy and total fertility appear to be associated or independent, right? And so here, right, when I can see some sort of pattern, then I'm going to say that they're associated, or there is a relationship, or there is a relationship. We also said, okay, just because there's a relationship, it doesn't mean that one causes a change in the other, right? We talked about that. But we can talk about if they're associated and if there's or if they're independent of each other. Okay. And then we don't have the link's not working, so we can't look at over the years, but you can probably hunt that down somewhere. They've probably improved it. Hopefully, it looks a little clunky to me, but whatever. Okay, so the side note here that I want to make is for any data visualization, we want to communicate as much information as we can without having to explain too much. Okay? So that's kind of a fine balance. We want to communicate as much information as possible without having to explain too much. For numerical data, there are lots of different visualizations that have been developed. We're gonna end up just focusing on one, which is histograms, but I'm gonna introduce a couple of others just so you've seen them, and then I can check it off and say that I mentioned it in class on my little spreadsheet. So we're gonna talk about them here, and then we're gonna settle in on histograms, which I'm gonna introduce last. Okay. And so to visualize the distribution, okay, that word's gonna come back to haunt us, okay? The distribution of one numerical variable we will use a histogram. Oh, why is it all glitchy? I think I need a new nib for my pen. We will use a histogram. But first, we will introduce a few other visualizations. So the distribution, if I give you, wouldn't this be so nice if I gave you each a bag of Skittles, let's say. Right, we all know what a bag of Skittles looks like. You open it, and then I ask you to report the distribution of the colors. I think intuitively you would know what to do then, right? You would sort them all into the different colors, and then what would you do? You would look at kind of how many of each color you had, right? And so that would be categorical data, but numerical data works the same, right? We're just on a continuous scale. It's just easier to think about sorting the colors, right? Instead of sorting maybe our heights into bins, right? And so, which is what we're about to be doing. Okay? So dot plots are one way that I don't really like. I have a lot of strong feelings about what I like and what I don't like. Dot plots I don't like. So you're allowed to not like them as well. And so one numerical variable could be visualized with dot plots. Now how they work is, let's say I have information on GPA, right? That would be a numerical variable, right? And so then every dot is this color to start. And then the more I layer on top of each other, right, the darker it gets. Okay? So the idea being that, okay, if you have some light colors here, that means that there are few observations there. Okay? And then as the dots get darker and darker and darker, right, that means I have more observations in those areas. Okay? If I had to kind of guess what this distribution might look like if I stacked them all on top of each other instead, which is probably more useful, which is the next thing, but I'd say probably something like this, right? Just going by the darkness, right? The darker areas have more dots, they'd be stacked on top of each other. I'm just gonna guess. That's really hard to do, right? I've seen this thing a million times and I know what it's going to look like, but that's hard for us to do. And let's go back to the key thing about a visualization is it shouldn't be hard to do, right? And so that's why I don't like it. We're going to talk about the distribution of the GPAs later with the histogram, or maybe with the next slide, because I moved the other one down. Right, but another option we have is we could, instead of layering the dots, right, and having to decipher where the darker areas are, right, we can stack them on top of each other. Seems reasonable. So each dot represents an observation, right, a GPA that's been recorded. Now, I don't know why they had this slide here, and every term I keep moving it down, I keep trying to, or remembering to fix it, and then after class, like, I'm done, and I don't do anything about it. So I moved it down if you're following in the slides that I posted. But here's a stacked dot plot. Same thing, same information, but I do think that it does a better job of showing us the distribution, right? And just like I said, we can kind of generalize this shape like this. Right? Notice that I'm not too hung up on the actual heights of the bars. I'm looking for kind of broad strokes, okay? And that's going to be coming into play when we're describing the shape of a distribution, which is one of our jobs, okay? And so, right, we kind of close one eye and just kind of go for it, right? Because this information is from a sample, right? A sample of GPAs, right? What if I were to release that sample and collect a brand new sample? Do you expect it to look exactly like this? Not really, right? Do you expect it, if I collect a random sample every time, do you expect it to look roughly like this? Yeah, right? Roughly, right? And so that's why we're using broad strokes, okay? Because if we are able to assume that this sample came from the population and is representative of the population, right? Then this is probably roughly what the population looks like as well, right? And so that's the goal. Okay, so we're going to focus on the shape for now, okay? But in order to fully describe a distribution, right? And this is a distribution of sorts, right? We talked about the Skittles. The colors of the Skittles is easier to visualize. You could even have a Skittle, 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 right? All stack all the colors, and you could look at the heights of each of the stacks, right? Now we're doing the same thing with GPAs. Here we've got this beautiful stack of 3.2s for some reason, right? And this one's a little bit off, but here's a beautiful straight stack at, I don't know, 3.3 maybe. Okay. And so, and then there's some jumble because they're not exactly the same, right? But roughly. So these are all distributions, right? Hey, they don't use the GPA data? Come on. I guess we were bored of it. No, let's have a look at what a histogram looks like. This is a histogram. Okay. And so here, we've switched the data that we're talking about. It's on the extracurricular hours. So I think it's the hours, or I know it's the hours per week spent on extracurricular activities of some student, presumably. Okay. And so what have we done, right? Instead of stacking individual data, right? For example, let's see here, this stack here, right? They're all roughly the same, right? There's some kind of jiggle in here, right? Where they're kind of off a little bit, but generally we can lump them in and put them in the same bin, it's called, okay? And so a histogram puts your numerical data, so the hours per week spent on extracurricular activities, puts that into bins, okay? And so this here is a bin. We still have this continuous data, right? These measurements, even counts, right? I can put them into bins, okay? So what that's gonna look like is it is kind of like the stacked dot plot, right? Because every observation adds some height. So here, at this point here, we have 50 observations. Usually it says frequency here, but the frequency is really the number of observations. So when we have a height of roughly 150, I can't tell if it's exactly, it looks like it's a little bit higher than 150, okay, for this bar. Okay. This is roughly 150 observations in that bin. In the 0 to 10 hours per week bin. Okay. Looking at this histogram, right? And I ask you, what's the most common bin, right? That's going to be the 0 to 10 bin, right? Most people are only able to spend 0 to 10 hours per week on extracurricular activities. Check out these weirdos. So much extracurricular activity time. Wow. I don't know what you would be doing. Not working, I think. Right? But these counts are very small, right? There are very few people who are able to spend a lot of time on extracurricular activities. Okay. So here, even the 30 to 40 group, that's a lot, right? And so there are very few people able to spend 40 to 70 hours per week on extracurricular activities. They're in the data, right? But most people are in the 0 to 10 category, and then it is decreasing as we move out, right? Okay. So higher bars represent where the data are relatively more common, right? But I think intuitively, if you look at this, you would, if it had kind of the frequency label there, you would get there, right? And so histograms are really useful for describing the shape of a distribution. Okay? And there are a number of shapes that we need to be familiar with. Okay, and so going way back, if I ask you what shape that is, well, that was a bad one. Let's say it's a triangle, right? This is a square, right? We all know these shapes. We just have to add a few more, okay? And so now the main one that we're going to be talking about is this bell shape. Yeah? So we're just adding it to our list of shapes that we know and love. And this is, we are going to call it a normal distribution. Okay? It's normal because it is normal. It's very, very common, but also it's the name of it. Okay. And so if we want to be fancy, we could call it the Gaussian distribution, but it's annoying to write out every time. So this is a new name that we're going to learn, the normal distribution. There are others, but for now, right, just kind of think of it that way, just adding a new shape to your vocabulary. Okay. The bin width. So here we have a bin width of what? 10, 0 to 10, 10 to 20, 20 to 30, 30 to 40, right? And so depending on how many hours per week you spend on extracurricular activity, right, you would be adding a layer all the way up to 150, right? And so the bin width, you can change the bin width. Let's do this here. The bin width here is 10. Okay. In Excel, you can easily change the bin width. Okay. It didn't used to be easy which is really funny because this is like kind of basic stats stuff. But now it's easy to change the bin width. And I always recommend going with the default, okay? Which is nice, right? But if you decide to alter the bin width from the default, right, there are a couple of things to keep in mind, okay? And so here, first, let's have a look at each of these histograms, which are on the same data, right, that we were just looking at. Okay? And from each of these, right, I would probably be able to get to the same distribution, but some of them are easier to read than others. Okay, and so let's talk about the bin width for each of these, starting with this one. The bin width, let's call it BW, is, in this case, looks like it's 45. I'm gonna just write here, I'll abbreviate this to BW, so I don't have to write so much. Oops. Hey, where's my eraser? There. Next one is the one that we were just looking at, right? It had a bin width of 10. Obviously, each of the bins have to have the same width, otherwise you're doing something weird, right? Here, the bin width seems to be 5. And here, what's the bin width here? Well, I'm able to have 1, 2, 3, 4, 5 bins in a length of 10. So it seems to me like we've got a bin width of 2. Remembering that these all show the same data, right? The data behind all these are all the same, right? And so now we need to have a look at these and figure out which one is best. And that's why I recommend just using the defaults, right? It'll kind of go through and do some internal calculations and set the defaults for you. And so you don't need to worry about this, but it's just good to see the effect of the bin width. So I think we're all comfortable saying that this one's a baddie, right? That doesn't tell us anything about the data, right? How about this one? I don't love this one. Why? Because it gets too nitpicky, right? It might make us think that there's a mode. We're going to introduce the mode, so a peak, right here when there isn't really one, right? It makes it look like that, right? Which is kind of misleading, right? So this one could be misleading. Unless you're really good at kind of squinting and just kind of broad strokes. But then you're better off, right, using one of these two. This one I would say is fine, right? I'm happy with that one, but I really like what I'm able to see with a bin width of 5. It tells the same story here, but with so many in the 0 to 10 bar, right? It might be nice to split those up, right? Turns out over 80 of those were in the 0 to 5 bin, right? And so being able to tease those out is kind of nice to see, right? And so what would you expect? The height of this first bar plus the height of the second bar should put you roughly at 150, right? Because it's the same data. And so I like this one, right? Because then we're able to kind of distinguish between, right, 0 to 5 versus 5 to 10, which is less common, right, within this original bin that we looked at. Okay. That all takes practice, right? I used to say that I was a professional eyeballer, right? So when I worked at a market research firm, I would do kind of the statistical analyses, and everyone's like, "Well, how did you know? How did you know to do that?" Oh, I just eyeball it, and so I was the resident eyeballer. But you know, you have to know what you're eyeballing and what you're looking for, right? And so a lot of it is just kind of, you eyeball it. I know. Sounds fun, right? Okay. I did do a sneak peek. I did say mode. Okay, and so the shape of a distribution, one of the things that we can use, or one of the terms that we can use to describe the shape of a distribution, is the modality. Modality, or mode, is really the peak, right? How many peaks do you have, right? And so there are a couple of options, go-to options. Usually we just have a single prominent peak, which we call unimodal, right? So one mode. Okay. All the clues in the names, right? Uni means one, modal meaning peak, one peak. Several prominent peaks. We can talk about bimodal. Bi means two, right? And then two modes. That's a specific case of just two modes, okay? Or multimodal, more than two modes is what I would say. Or no apparent peaks, which would make it uniform, right? So in terms of what these things would look like, okay, and to emphasize that you don't want to get lost in the weeds here, right? And so in the weeds, which is it? Reeds, right?
Yeah, I think so.
Yeah. If I say it fast enough, you won't know what I said. That's my best trick in the book. You don't want to get bogged down by nitpicky things, right? Broad strokes. So, let's see here. She's got this very elaborate kind of thing. So in order to determine modality, step back and imagine a smooth curve over the histogram. Imagine that the bars are wooden blocks and you drop a limp spaghetti over them, right? There's still some structure there. And so it's not just going to droop down, okay? And then the shape the spaghetti would take could be viewed as a smooth curve. Okay, so really, really eyeballing it here, right? I would say it looks like this. This looks unimodal to me, right? In our sample, yes, we have two peaks, but they're not worth mentioning, right? Because if I took a new sample, I don't think I would see the same two peaks here. Okay, so this I would say is unimodal. The next one I can't really get away from, right? I will have kind of two peaks. Okay? And so if I kind of drop my spaghetti on there, I used to think of a sheet, but I think a limp spaghetti is a little bit funnier to think about. So here I have two prominent peaks, so I'm going to say it's bimodal. This next one, I could be convinced either way. If you wanted to say, okay, this one's a peak and then these can get smudged together, I would personally be okay with that, okay? But I also happen to know that she wants us to see a multimodal distribution. And so let's make that happen. Something like that. But like I said, I would actually personally be fine with something like that. All right. And so here I'll say multimodal or bimodal again. We will only analyze unimodal distributions. And so that's why I'm kind of wishy-washy on this stuff. We won't have the tools to analyze anything but a unimodal distribution. And so it's okay, just know that they exist and broad strokes only. Even this one, right? If I kind of drape my limp spaghetti here, right? Then we're supposed to say that this is a uniform distribution. I agree, but I think we could have gone more uniform than that. Maybe something like that. Okay. So uniform means that there's no peaks. It's just the counts are all the same, right? And so thinking about your bag of Skittles, man, I really wish I had brought a bag of Skittles for everyone. Right? If I ask you, are the colors in your bag uniform? You would probably have your colors stacked. And if all the stacks were about the same, you would say yes, right? Same thing for numerical data, right? It's just easier to think about categorical data. Okay. So for us, we're going to focus on unimodal distributions. Okay, so our analyses will focus on unimodal distributions. Okay. Would you believe it if I told you there's more to the shapes than just the modes? We can also talk about the skewness. Okay. So skew is, a term that we might use just in kind of regular language. Okay. And what does it mean? If you were kind of pressed to think about what skew means, it means kind of swayed in one direction, right? And so one of the things that we have down here, and I always forget that it's down there, so I'm kind of proud of myself there, but kind of counterintuitive, okay? Because the skew, when we talk about the direction of the skew, it's always in the direction of the tail, okay? So kind of where are the fewer observations, right? Which are the less common observations, okay? And so the skew of a distribution, and maybe I'll say of a unimodal, because we can only have skew if it's unimodal. The skew of a unimodal distribution, is in the direction of the tail. That, to me, at least, was counterintuitive when I was learning this stuff. Okay, and so if I'm dropping my limp spaghetti on this first one, it would look something like this. Right? This is my tail. So it's skewed in the direction of the tail. So it's skewed to the right, or you can say a positive skew if you prefer positive, negative, doesn't matter. Okay. I'm gonna call it right skewed, left skewed, or skewed to the right, skewed to the left. Okay. But this is skewed to the right. Okay. So in the direction of the tail. Okay. Whereas I think humans tend to want to talk about, okay, well, this is where most things are happening, right? So it's skewed in this direction. But in statistics, we're more interested in those extreme observations. They're the ones that we want to analyze. Okay, and so that's why it's skewed in the direction of the tail, the more extreme observations. Same thing with this next one. If I drop my spaghetti here, I would say I've got a tail to the left. Right? And so this is skewed to the left, or left skewed, or I'll introduce kind of all the options here. Negative skew. One of the reasons I'm a slow marker to begin with, but one of the reasons it takes a long time to mark stats is because as long as what you're saying makes sense, there's no like obviously right answer immediately. I have to read everything that you're saying and it also makes sense, and you have to follow through and all this stuff. But there are a lot of things that you could say. So I'm going to call it skewed to the left, but you're allowed to say negative skew. I will understand. Okay, and so just kind of takes some effort on my part, right? Usually by the time test one, or are we calling it a test or a quiz, or what did we land on? We don't want to call it something scary, right? Your first inventory of knowledge rolls around. We'll have moved past this. This would be kind of a multiple choice question, right? And so I'll test you on it, but make it multiple choice. I know, cheating. New phone, who dis? How about this next one? If I drop my, I don't think it's skewed in any one direction, right? In fact, I would say it's symmetric about the mode. Okay, and so here I would say that this is a symmetric distribution. Symmetric, I'll add in brackets, about the mode. Right, around the mode is what I mean. But usually we say about. Which sounds funny now that I declare it out loud. But we do. Okay. So being able to look at a histogram and figuring out if it's skewed, and if so, which direction is it skewed in? So like I said, one of our main things that we're going to be interested in statistics is unusual observations or outliers. Okay. And so are there any outliers in these distributions? So in the first one, I would say, yeah, there are, right? There's a few over here. Okay. In the probably 18 to 20 range-ish, right? Depending on the bin width, can't really tell. Looks like they're 2. If I had to guess, there are only, right, this many. Let's see if I can pull this off. Is that 1/5 of 5? I don't know. Is that 1 observation or 2? I don't know. Doesn't really matter. 1 or 2, right? Outliers, if we had the data, we could just go find them and count them, right? But so I would say there are some outliers. There's a visible gap there. I would call these outliers as well. There's a few more, right, than before. Okay. Doesn't matter what the data is here, right? These I would consider outliers. Eventually, right, we are going to develop, I think we won't get to it until Friday, but we will have tools that say because these numbers are bigger than this value, then they are outliers, right? So we will have kind of concrete ways of determining if we have outliers. But the first thing to do is to look at the distribution and just kind of, do I suspect there are outliers? Okay. Outliers are important because they could indicate kind of interesting observations, right? So there are a couple of different options here. Outliers could be interesting observations. They could be data entry errors. Or they could just be due to random chance. We don't really know. Due to random chance, depending on what we're talking about, right? So we don't really know, and that's why we need to investigate them a little bit further. Especially if it's a data entry error, right? A GPA higher than 4, for example, right? That sounds like a data entry error to me. Yeah. Side note, has anyone read Outliers by Malcolm Gladwell? Malcolm Gladwell, if you've read any of his books, they're like stats for fun. So he uses a lot of stats in his books, and I really enjoy him as an author. But Outliers is particularly good. Okay. It's been telling us to describe the shape and all these things, but now is the first time that I'm going to tell you what I expect when you're describing the shape or describing a distribution. So here, to fully describe a distribution, and I guess I can start over here. Whoop. We need to discuss these 3 things. There are 3 things to fully describe a distribution. We need to discuss 1, the shape. Huh? I'm going to start with, is it, usually I'm supposed to just talk about unimodal symmetric, right? A unimodal symmetric distribution, right? Looks something like this. But we already know that shape. I already said this is the normal distribution. But it is technically unimodal and symmetric. But I think we're there, right? Being able to talk about a normal distribution. And then all the other shapes I would first categorize as just non-normal, right? Having this only two options I find is really helpful. I capitalize normal mostly to emphasize that it's a name, right? You can use a lowercase, that's fine. But right, especially as we're starting, right, I'm going to capitalize normal so that you start to think of it as a name. Okay. So normal, versus non-normal. That lets you lump everything else, right? We'll explore the non-normal distributions, right? But really what we're going to focus on is unimodal distributions. So they're either skewed left or skewed right, and then that's it, if it's non-normal. But you need to talk about the shape. And you don't want to be too nitpicky either, right? Broad strokes. In fact, I'm going to, unless it's very, very obvious that it's non-normal, right? You should be pushing for a normal distribution, right? And so the reason for that is all our analyses rely on having a normal distribution. So if you tell me it's non-normal, that kind of puts the brakes on everything and we can't do anything in this course. And a lot of things are normal. And so it is reasonable to kind of argue that you can assume a normal distribution. Okay. So the shape, the next thing we need to talk about is the center. Approximately, where is the center of the data? Okay, so rough approximations. Thinking about, okay, is it centered on 10 or is it centered on 100, right? Kind of the scale of your measurements. Okay. And so 10 versus 100, for example, right? Just to get an idea of where most of your observations are hanging out. Okay. And we will have calculations to calculate the center, right? And so we will have actual centers, measures of center, but if we're just describing the distribution, we're just getting an idea. Okay. And then finally, the spread. Usually I just kind of mention the minimum to the maximum. Okay. The minimum to the maximum. Again, rough approximations, very rough, right? And so roughly, because again, we're going to have a numerical measurement for the spread, right? And so we will be able to kind of calculate the spread. So here we're just getting an idea of information. Okay. So, okay. How would you describe the shape of the distribution of hours per week students spend on extracurricular activities? We've already practiced this. First, let's talk about the shape. I would say this is skewed to the right, right? It's skewed in the direction of the tail. Okay. So it's skewed right, or positive skew if you prefer. The center, again, just kind of an idea of where most of your data is hanging out, right? Where is the peak essentially, right? And so here we don't have a ton of information because we're using the 0 to the 10 bin width, right? And so I would say the center, most of these data points are in the 0 to 10 range. Center 0 to 10 hours per week. And then the spread is just kind of, okay, well, what was the range of the data that you saw? I would say 0 to 70 hours per week. The idea being, if I just gave you this information, you should be able to imagine this shape, right? So as I'm gonna add a page here. Hey. Oh, no, you don't. I need lines. There. Good. So as an example, imagine you're on the phone with your friend. Banana. There's this joke study that they did where the banana is the preferred fruit for pretending it's a phone. Gave a fruit bowl, asked everyone, okay, use one of these fruits to pretend it's your phone. Everyone grabs a banana. Anyways, so you're on the phone and I tell you, you won't believe this. I'm looking at a normal distribution. Okay, already you have an idea of the shape. Well, you should. Something like that. Right. Looking at a normal distribution, okay, that's cool. Pretty common, not impressive, is what you would say to me. I know, but it's centered on 30. Yeah. Centered on 30. So then, okay, you're kind of sketching, you're on the other line and you're sketching out, okay, so probably roughly 30 there. Okay. And it ranges from, I don't know, ranges from 10 to 50-ish. So 10 to 50. You have a pretty good idea of what this distribution looks like, right? Just from those three things. Now, if I told you, yeah, but there's one observation that is at 75, knowing the distribution, right? You would say, oh, that's weird, because 75 would be way out here. Huh, not really where I would expect to see an observation, right? And so that's the reason we have to be able to kind of describe this distribution, and that's what we're going to be using the distribution for, is to determine, okay, is this an unusual observation, or is it just kind of run of the mill? And then you could say, oh yeah, you won't believe this, I found an observation that was at 20, right? Then I don't know, that'd be somewhere here. That's not interesting, right? That's hanging out where you expect data to be. And so, right, just lets us figure out if things are kind of unusual or not. Yeah. So maybe, just maybe, I can scooch this down. I'll keep going with my number line. Doesn't matter what it is I'm measuring. Put the 75 on there. Maybe I don't need a full page now that I've written it all out. Whee. Tiny. Good.
Is the skewed distribution still a normal distribution?
No, it's unimodal, but the normal distribution has to be unimodal and symmetric. Yeah. And so we could do a similar example where, let's say it's skewed. Let's do the opposite of the other one. Skewed left with a center around 10 from 0 to 15. This one's a little bit harder, right? Kind of imagining, okay, so let's start with the shape. It's skewed to the left, which means you've got a tail on the left. And the center, kind of the peak, is at 10. And we're going from 0 to 15. But again, if you said, oh, I found an observation at 25, right? Knowing the range, right? That's kind of extreme. Even an observation of 2, right, is kind of unlikely, right? Even though it's within the range. Nice. Here's a summary of the shapes that we've talked about. And so we talked about modality. So the number of peaks, we can have a unimodal distribution, right? We can have a bimodal distribution or a multimodal distribution or a uniform distribution, which has no peaks at all, like we said. And then from the unimodal distribution, if we have a unimodal distribution, we can talk about the skew. We can talk about the skew. So it can be skewed to the right, skewed to the left, or symmetric at the peak or about the peak, about the mode. Right. And this little guy, right, if it's unimodal and symmetric, we call it a normal distribution, right? It gets its own name. What's fun about the normal distribution is a lot of measurements follow a normal distribution, right? And so if we think about kind of heights, right? Heights in a general population, right? Then we know that most people are kind of, you know, within the realms of average height, right? Should probably split the population, right? Males, females, because females tend to be shorter, right? But then I would just have 2 normal distributions just slightly off of each other, right? But right, in general, we're all kind of hanging out in this lump. And then there are a few very, very short people, right? And a few very, very tall people. So if I tell you, oh, I met this girl and she was 7 feet tall, you would say, whoa, that's unusual, because you have an idea of what the distribution of heights for females looks like, right? And it is normal. Okay. Which of these do you expect to be uniformly distributed? Yeah. So weights of adult females, I would say would be roughly normal, right? Because if you're, so they're kind of linked to your height, right? If you're short, then you tend to weigh less, and if you're tall, you tend to weigh more. And if you weigh average, or if you're average height, you also tend to weigh about average, right? And so, of course, there's kind of variability there. I know it's a buzzword in statistics, right? Variability that we need to manage. But I would say that the weights tends to be approximately normal, right? We'll throw the word approximately in there for good measure. Yeah. Approximately normal. Salaries of a random sample of people from North Carolina. Okay. And I'm going to lump it in with the house prices because anytime that you have money, money tends to be skewed. Okay. And so salaries and house prices, sadly, money tends to be skewed in the same direction, which is what? Skewed to the right, right? And so money in general, money tends to be skewed to the right. There are instances where it's not, but thinking about salaries, and if I kind of do something like this, seems reasonable, right? So the salaries of a random sample of people from North Carolina, right? A lot of people make kind of down here, and then very few people make a ton of money, right? Same thing with house prices. Most house prices hanging out down here, right? And then you've got the odd one, right? Where you've got this very expensive house, right? And so house prices, as soon as you're dealing with money, you're not necessarily going to have a normal distribution anymore, right? Which leaves us with the birthdays of classmates, the day of the month, right? And so if we think about the first, the second, the third, the fourth, the fifth, blah, 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 of course, kind of towards the end, it gets a little messy, right? Because the different months have different lengths and things like that. But generally, I would expect a uniform distribution. There's nothing that says, oh, you're more likely to be born on the 5th, right? Oh, you're born on the 20th. Oh, aren't you lucky? That's so special. No, it's all uniform, right? So here, or maybe if we're being kind of more reasonable about it, right here, 1, 2, 3, ba, 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 ba. Let's do 28, 29, 30, 31. I would expect it to look something like maybe like that. Fewer months with those number of days. Right. But that's picky. I would say it's uniform, right? Broad strokes. Broad strokes, uniform, which means I'll pick that one. Okay. So being able to think about the information that you're about to collect and what the shape could be, right? That's going to help you determine how you will be able to analyze things, right? So if you want to analyze money, then maybe you want to talk about it in terms of a categorical variable. That's an easy kind of get around, right? or if you really want to talk about nope, don't say it, Emily. I'm giving it away. If you really want to talk about a measure of center, which is usually the average, right, for numerical data, you can't if you have a skewed distribution. Okay, so that's the reason we need to be aware of it. Okay, so all these reports that you hear about the average house price, for example, that doesn't mean anything because it only works if you have a normal distribution, right? So we should be talking about the median house price, which we'll talk about on Friday. Okay, I'm gonna skip this one because I can't tell. Okay. I never know if I can rely on the clock or what, but it looks like I can. You can try this on your own, but sketch the expected distributions of the following variables, right? Number of piercings. Okay, fine, let's do it. I just don't want to do this one. Because we already talked about it. I'll write out what it should be. Number of piercings, right? A lot of people have 1 or 2, that's pretty common, right? And then 3 piercings, okay, sure. 4, all right. 5, well, that's kind of a lot, right? 6, oh wow, can happen, right? But what's that distribution gonna look like? Skewed to the right. Scores on an exam tend to be normal, right? Depending on the course, right? I often see distributions like this. What does that mean? A lot of people are kind of up here, right? You came to class, you did the assignments, you're doing it, and you've learned some stuff. And then usually these folks down here, they came and wrote the test, didn't go so well. They tried their best, but it didn't really pan out, right? And so there's a smaller subgroup that's kind of hanging out on its own. And so, but most people are kind of up here with the odd 100%er. I always make sure that someone gets 100%. And so I adjust the total if I don't, but someone should get 100%, right? It could be you. Wow, I know. I shouldn't have made this lump so big. It tends to be a very, very kind of small lump, but don't be one of these. Be one of these. Maybe be one of these. Ah, nice. IQ scores, again, tend to be normally distributed. All right. No reason for them not to be. We've got this average IQ that we're all centered on, and then we've got some rare instances in both directions. Generally symmetric. Come up with a concise way to teach someone how to determine the expected distribution of any variable. I think that's kind of, you can try to think about it, but just like we did, you kind of think about where your most common observations are, and then where some rarer observations might be, and then you have it. So I guess I did it. This one is moved from the beginning. Remember that slide that I had, how I moved it. Now here we are. What I want to save though, here, use this space, is So to describe a distribution, we need to talk about the shape and the center and the spread. And just as I mentioned, right, we will be able to calculate numerical measures of center and spread depending on the shape. And so we will be able to calculate numerical measures of center and spread depending on the shape of the distribution. Depending on the shape of the distribution. So we're going to start with assuming that we have a normal distribution, right? Or a unimodal symmetric distribution. So a normal distribution versus a non-normal distribution, which can look like this or like this, more or less. I'm going to try to squeeze it in here. Depending on the shape, the measure of center or the appropriate measure of center for a normal distribution is called the mean, which is also the average. But in statistics, we tend to call it the mean. Yeah. But if you say average, I'll know what you mean. And sometimes or often I use average just because it sounds better, right? And so, and sometimes I'll say the mean because it sounds more natural to me, depending on what I'm talking about. Okay? And so the mean only applies if you have a normal distribution, right? The thing is, you'll be able to calculate the average even if it's a non-normal distribution, right? So that's the caution, right? And that's why we see so many articles where they're reporting the average of skewed information, right? And so, and that's bad. You don't want to do that. But what should we be reporting on? We should be reporting on what we call the median. I suspect we won't get to talk about the median until next day, but because we'll start with the mean and the normal distribution, right? And then we'll go to the non-normal distributions. But the median is just the data point that splits your data in half, right? That's useful, right? Because then you're kind of ignoring these extreme observations in the skew, right? And so then it's just the data point that splits your data in half. The spread, if you have a normal distribution, is usually we are going to use the standard deviation. Which in text, I'll abbreviate it SD, okay? But in calculations, we use a lowercase s. Okay? Or S in calculations. We usually don't want to have more than one variable in our calculations, and so that's why SD doesn't really work. But so we just use a lowercase s. Okay, if we're going down that route, what's the notation? It's on the next slide, but the notation that we'll use for the mean and to calculate the mean is going to be x bar. So it's a lowercase x with a bar over top of it. In fact, anything with a bar over it, anything with a bar over it denotes a sample average or mean. Denotes a sample average or mean, which makes this your average smiley face. Tee-hee. Oops. I almost wrote skew. That's wrong. So anything with a bar over it. We tend to use x just as a placeholder for whatever variable we're talking about. But if we want to talk about the average GPA, right? This is the average GPA, right? Whatever it is you want to talk about, you just put a bar over it, remembering that it is the sample average, denotes a sample average. Yeah. The median doesn't really have any notation that we use. You can use an X with a tilde over it, which would look like this, but I never use that, so I'm not going to. So a tilde is just a little, it's a tilde. I don't really use this, so I'll put a slash through it. It exists if you want to. But usually I just write median equals whatever. If we have a non-normal distribution, then the measure of spread that we're going to use is called the interquartile range, or the IQR, the interquartile range. It's going to take us a while to get there, but we can use the words against themselves, right? Inter means between. Quartile, if you had to guess, okay, maybe if I split my data not in half but into quarters, right? Then maybe it's the distance between the first quarter and the third quarter, which it is, right? I'm not leading you astray here. And so the interquartile range is the distance between the first and the third quartile. We're going to get there, but just so that you have an idea of what it is we're doing. Okay. But for now, we're going to focus here on the normal distribution. Okay. But like I said, the important thing is that you recognize that, okay, you can make Excel calculate any of these values for any numerical data, right? But they only apply in some instances, right? So the mean only applies if you have a normal distribution, and the median, although you could use it in a normal distribution, the mean is more powerful. There are more things that we can do with the mean, and so then you should be using the mean instead. But the median is the one to use if you have a non-normal distribution, and same with the spreads. That's a lot. Any questions? Let me think about it. I know. Okay. Before we look at this calculation here, it's not that crazy, but I do want to highlight that you already know how to calculate the mean right? How do you calculate an average? If I, for example, had some variable x, right? Just a generic variable x, and I told you that, okay, I saw a 3, I saw a 5, I saw a 7. I'm not very creative, but let's throw an 8 in there. And I ask you, hey, can you do me a favor? Can you calculate the mean of x? What would you do? You would probably, right, say, okay, then I'm going to take 3 plus 5 plus 7 plus 8, and then you're going to divide it by 4, right? And that's the mean of x. And so x bar then is 3 plus 5 plus 7 plus 8 divided by 4, which is really what? Your sample size. I had an itty bitty sample size of 4, right? So we divide by n, the sample size. In terms of kind of referencing these observations, right? Under x, I have the first observation of x. I have the second observation of x. I should do it this way. I have the third observation of x, and then I have the fourth observation of x, right? And so in general, what can you do? You can write x1. Usually we use a subscript 1, x1 plus x2, all the way up to xn, right? Add up all the values in your sample, and then divide by your sample size. I was going to bring you the formula sheets. I know. I forgot though. I'll try to remember for Friday. Something to look forward to. So x bar can be summarized not just as x1 plus x2 plus blah, 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 all the way up to xn divided by n. We can introduce what we call summation notation. Fun to say, fun to do. The sum of x is how you read this. So this is a capital sigma, okay? And it means the sum of all your x's, right? Add up all your x's and divide by n, right? That is, this here is the sum of x. I like to do a little fancy x, a little curl, a subtle curl. So even more condensed notation is the summation notation, right? Which is that capital sigma. And let's see here. If you're unfamiliar, you can look up summation notation. But it really just says, add up all the things that I have a sigma in front of, right? Add up all your x's. Which, as we saw, you know how to do, right? And so it's nice to see a link between something that you already know how to do and then kind of bake it into potentially new notation, right? The summation notation. I'm not going to test you on your summation notation or anything like that, but it is something I want to pick through and because it's going to come up more than once for sure. And so we need to be sort of familiar with it, right? Not 100% confident necessarily. I'm not going to make you even calculate the average necessarily on a test, right? Probably on an assignment though, but you're allowed to use Excel or whatever you want, right? So this X here, this was a sample, right? Same with this sample here. It's a sample of size n. And so X bar is really only for I already wrote it, sample mean, right? Okay, this is where we need to really kind of stay on top of things, okay? Because our goal in statistics is to take a sample and do calculations and things and learn about the sample. But really what we're interested in is learning about the entire population that we drew that sample from, right? Which means that we're going to have a sample mean, but we're trying to learn about the population mean, right? So we need different notation depending on where this information came from. And so the population mean is denoted by a mu, a Greek letter mu. It's got kind of a long tail on the left, and then it's just a fancy M. And oops, not new. It's spelled M-U, mu. Yeah. Now the mu is denotes the population mean. For anything we calculate, there will be that that kind of symmetry, right? If I calculate a sample mean, then I'm trying to learn about the population mean. If I, let's go back here, calculate the sample standard deviation, there will also be a population standard deviation that I'm trying to learn about, right? And same thing with the median and the IQR, but let's focus on the mean and the standard deviation for now. Okay. And so we're going to have this little brother, big brother situation always, right? But that makes it really hard because there's a lot of notation that we need to keep track of. As a rule, all the Greek letters are from the population. Okay? They get fancy names, and anything from a sample is denoted by just kind of regular letters that we're used to. Okay. So Greek letters are for population parameters. Okay. If it's a measurement from the population, we call it a parameter. I'll write that down here. Measurements from the population, which we don't tend to have measurements from the population. If I knew everything about my population, why would I try to collect a sample to try to learn about what it might look like, right? It's over. I already know what it looks like. So measurements from the population are called parameters. Notice the P and the P versus measurements from the sample. From the sample are called, you won't believe this, they're called statistics. From the sample are called statistics. And notice the sample statistics, the S and the S again, right? So the sample mean is a sample statistic. Right? kind of redundant to say sample statistic. If you say statistic, it's implied that it's from the sample, but usually we do anyways just to emphasize. But it serves as a point estimate. Okay. And that's going back to this idea that, okay, if I have collected a random sample, I'm allowed to assume it's representative of the population. That's great. But if I went out and collected a brand new random sample, it would be slightly different, right? But still, hopefully a good representation of the population. And so it's a point estimate of the population mean, right? And this term point estimate, we're going to rely upon quite a bit. So we'll get used to thinking about the sample mean as a point estimate for the population mean, right? It's my best guess that I have based off of my sample. So this estimate may not be perfect, of course, we understand. But if the sample is good, representative of the population, which is really just kind of code words for randomly sampled, it's usually a pretty good estimate. So it all goes back to the sampling, and that's why it's so important. Okay. So like I said, we're gonna have this kind of population situation, and then a sample is a subset of that population. All right, so here I've got a sample. And in terms of the mean, I calculate a sample mean X bar, but really what I'm trying to learn about is mu. Right. So they're gonna go hand in hand. I probably should have written that on a separate page, but squeezed it all on there. Luckily, I post my notes after. Thanks. But can you imagine reading the notes and you weren't here? What a mess. And then there's this thing, I don't know. So for our measure of center, that's it. Let's end there. We'll pick up here next day where we'll talk about measures of spread for a normal distribution. All right, if you have any questions, let me know. Otherwise, I release you.